Hello everybody, how's everybody doing? Hope you're doing fine. Okay, I just want to announce first that on Friday I'm going to have a little interview for those of you who are interested in understanding a little more, maybe, perhaps, depending on how the interview goes, about the extinction of man, the very likely upcoming imminent extinction of man theory I have now for 20 years. Well, then you can tune in. I'm going to be putting a link in Patreon and in Facebook. So those of you who follow me there, well, you'll know how to tune in. Anyways, that's going to be on Friday. It's going to be at 6 o'clock in the evening UTC Zulu time. Okay, so if you're interested in the extinction, what this coronavirus thing will be triggering, possibly, then it's a good time to tune in. Anyways, what I'm going to talk about today is about motion and how it's changed through the ages. And it's really quite funny to see all the notions of motion that we've had. I'm going to start with a comment. Someone made a comment on the word concept, okay? And I want to clarify that, okay? So here's the comment. It says, can't a concept be described by one object plus a concept? A day-old apple, for example, right? The same apple that is 2 days old. Do you mean that in this case the apple is two objects, or does the one apple object, right, and the passage of time concept define a concept specific passage of time? Yeah, we have to remember that a concept is already a relationship between two objects made by a conscious observer. So a concept already embodies objects. So yeah, you can say that you can compare an object against a concept, if that makes any sense. But the concept itself already has two objects in it. Okay, and yeah, and here's a pictorial representation of an answer to this fellow's question. Here you have, this is motion, but it applies anyways. Here we have a movie of motion. We have three frames in this film strip, okay? And so the issue here is that that box is the same box in each one of the frames. It's just at different times, different locations, right? It suffered motion. There's different distances between it and, assuming all these other objects are standing still, completely still in the universe, it's moving with respect to them. It's changing its distance with respect to each one of those objects. So yeah, it's the same box, and what we would be comparing is the box on the, in this case, in the third frame with the one on the first frame. We're treating them as two separate objects simply because they have different locations. We're talking about two things. We're making a comparison. You can only compare two. You can't compare one. If you have a single box in the universe, that's all God made, there's nothing to compare it with. There's no distance because, again, distance is a concept that requires two, okay, objects. And here there's only a box. So it has no location. Again, it requires more than one object, etc., etc., etc. So, yeah, if you match it against a concept, there's no difference, really, okay? No change there. Okay, let's get on with it. I left the other day with good old Aristotle, and I'm just going to summarize his notions of place, first of all, of object, of what an object is, then of place, time and motion, okay? And so here they are in a nutshell. This is what I've covered last couple sessions. What's a body or a thing, an entity, a medium? Okay, because all those words mean the same thing in physics according to rational physics. And it's bounded by a surface, and that's pretty good. I've got no problem with that. That's at least very close to the definition that we're looking for. Unfortunately, he didn't pay any attention to it. Nobody did in ancient times. They never realized how important that word was for the purposes of physics. You need to have an object, a body, a thing in order to do physics. You can't do physics without a thing, with absolutely nothing out there in the universe. They never figured that out, okay? And so they always kept inventing this ether stuff, the little particles that are in the background, because they never knew or never understood, never figured out what space is. Okay, that's it. Place, what is place? Place is the boundary of the body, which contains it. Okay, so he's saying it's the hole where you put the ball. And when you pull the ball out and you leave a hole, well, that's the place. But it's only a place when the ball is in there. When you remove it, it becomes a void. So there's a difference between in Ari's language, right, between void and place. Okay. Okay, and he continues, just in case you missed it, he says, place is the boundary itself, okay? And here he specified so that you can't miss it. Place can be left behind by the thing and is separable, okay? So it's the hole that you leave behind. That's called place. Time, what is time? Time is a measure of motion. Okay, measure of motion. Time is number. I think the translation is wrong. I put amount there. I think it sounds better. It's amount of motion. Okay, and he clarifies. Time is not movement, but only movement insofar as it admits of enumeration. Okay, what is motion? Change of place. What's the problem there? The word change. Change is already motion. And that's essentially, you know, where he made his well, one of his errors, okay? But everybody who inherited this stuff from him ended up, you know, using the same, essentially the same definitions. Here you have the modern definitions side by side. Well, not side by side. It doesn't matter here. What is an object? Anything. These are definitions from dictionaries, Wikipedia, etc., right? And the ones you'll find on the internet, the first ones that appear. So this is the notion people have out there. And these are the notions that the mathematicians use, okay? Because you won't find a definition for these words officially out there, okay? Anyways, object, anything that is visible or tangible. Absolutely not. That's not what an object is. But in ordinary speech, you can say that, not in science, not in physics, okay? An object is that which has shape, not that which can be touched or seen, okay? But you can see that those are the definitions they have. Object, a material thing. I like the fact that they're using anything, thing. They're using synonyms to define whatever we want to define. You can't use the word thing to define the word thing. Object is a thing, so you can't use the word thing. A material thing that can be seen and touched. And the other issue is material. Material is always a bunch of objects that exist. So it's material is just a bunch of objects. So you can't use that word either to define the word object. Another one, object, collection of matter. Again, matter, you can't use that word because matter is objects. Okay. And collection is wrong also because that's mereology. That's saying that a table is a billion atoms and I don't know, maybe a ball is also a billion atoms. So what's the difference between these 2 billion atoms if an object is just a billion atoms? What are you going to do, count them or what? So you can't use mereology. You can't say an object is what it's made of. That's mereology, okay? It's religion. Position, which is the more or less the notion, I guess, that Ari wanted to convey regarding place. He says a Euclidean vector, vector's motion, and they're going to describe position, which is supposedly a static concept. They're going to define it in terms of vector, which is displacement, okay? That represents the position of a point. I like the fact they use a synonym, position, to define position. What's a point? It's also a position because it's a location, right? It's what you put to designate a location. You ask them, what's a point? Well, here's the dot. What is the dot? Well, it's really representing the location. So all these are synonyms. They're circular definitions. Not one of these passes scientific criteria. Motion is the change. Again, where they get that? From good old Ari. Nothing changed in 2,000 years. Okay, changing the position of an object over time. They use the word time to define motion when motion should be defined before time. What is change? Also something blah 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 time. So these people are defining motion in terms of time. So how are they going to define time? Well, hopefully they define in terms of motion. So they're going to have a circular definition. You can't use the word time to define motion. What's time? The system of those sequential relations that any event has to any other. Time is the indefinite continued progress of existence, okay, and events. Time as the progression of events from the past to the present into the future, whatever those are, because past, present, future already involve the word time, embody the word time. So you can't use those words to define time. Time is defined by its measurement. This is these last two, by the way, are from physics, supposedly physics, mathematical physics. Defined by its measurement. Time is what a clock reads. Well, I don't know. My clock is illiterate. Never went to school, so my clock doesn't read anything. So yeah, we don't have rational definitions from the mathematical establishment. That's a big problem because it shows that these people never learned how to define words scientifically. That's what it stands for. That's the result today. We have no definitions for these words. No scientific definitions. Now, we don't care about the word time because we have no use for it in physics. That's in religion where they use the word time. In physics, in science, you got to explain a phenomenon. Time does not help us explain any phenomenon. Time is a mathematical description of whatever. And we've already defined time, so I'm not going to go over that. But it's a mathematical description. It's a number line. That's what it is. That's what time is. Okay? Comparison of two motions. Okay, things did not stay like this forever. Some people did analyze Ari and also Plato and some of the other Greeks. And Aristotle, because he was probably the one who did the best job in putting all this together, and because we found his books. Because we have no books from Democritus, and they say he wrote just about as much or maybe more than Aristotle. Okay, so one guy that analyzed Ari was this guy here, St. Augustine of Hippo, okay? And he said the following, very interesting way of thinking, okay? He says, "Let no man then tell me that the motions of the heavenly bodies constitute times," okay? Because when at the prayer of one, and he's going to refer to Joshua when he prayed for the sun to stand still in the sky, the sun had stood still till he could achieve his victorious battle. The sun stood still, but time went on. Okay, so what was this all about? Well, his reasoning is, look, you've got the heavenly bodies, you know, and the sun, at least in the flat earth, goes over the over the sky, right, and moves around, right, and comes back the next morning or whatever. Okay, so the sun moves, right, around the earth, and so does the moon, right? That's how these guys were looking at this, right? And, you know, Joshua told the sun to stand still, or at least asked God to make it stand still. God conceded his wish, and he was able to defeat, I think it was the Philistines, right? And so what happened? Well, the sun stood still, and they fought. So, you know, we had no motion of the heavens, which is how we used to measure time, right? But there was still, I mean, you know, we had motion there, and the motion had stopped, but time went on. And so he suggests, and that's going to be taken over also by St. Thomas, who comes in next in the analysis, when you know, you have this motion going on, now it's stopped, time continues, and what these guys are going to have in the back of their mind is that motion belongs to the object. Time is something external to the objects, okay? Other than decay, right? But in general, when we talk about time, we talk about something external to the objects. The object who does the motion is, like I said the other day, the moon moves, but you ask the moon how much time it took, the moon has no idea. The moon makes no comparison. The moon only knows that it moves. And that's all that we have out there in the universe. We have motion, but time is here, down here in our brains. There's no such thing as time up there, you know, moving around or doing something, okay? So It's important to keep that distinction. Okay, here's Tommy, St. Thomas Aquinas, okay, and he did a little bit of analysis on motion and time as well in Summa Theologica. Matter was in some measure formless. Remember, these guys get a lot of this stuff from the Bible, okay, so keep that in the back of your mind. Matter was in some measure formless before it received its full form, okay? Silly putty, you mold it, right? So time was in a manner formless before it was fully formed and distinguished into day and night. You know, God separated day from night. He says that in the Bible, okay? Time is nothing else than the measure of priority and succession of movement, okay? So again, these people are relating it to motion, okay? That's important, but it's the measure of motion. That's what he's saying that time is, and that's more or less the notion we, the mathematicians have today. Among the first created things are to be reckoned those which have a general relationship to things, and therefore among these time must be included as having the nature of a common measure, but not movement, which is related only to the movable subject. Okay, objects move; they don't do time. Only prisoners do time. Okay. That's his logic, essentially, okay? He's saying, time is not exactly the same as motion. There's a little bit of difference, but they never figured it out. They never realized what they were saying. They never had a definition for their own word for time, because we don't use time in physics. But obviously, these people in mathematical physics and in religion, they like time so much, well, then define it, And this is what he says next. Here we have kind of like wrapping it up, right? Places implied as existing in the empyrean heaven, okay? This being the boundary of the universe. So if you always wanted to know if the universe has an edge, yeah, it is. The edge is known as heaven. And since place has reference to things permanent, it was created at once in its totality. God did it all at once, okay? But time is not being permanent. It's always moving. Was created in its beginning, the beginning of time, right? Even as actually we cannot lay hold of any part of time save the now. Okay, so that's the only part we can experience, the now. We don't experience the whole interval of time from past to future. We only, except maybe in our brains, we remember, but we live or experience at the cutting edge of time. You can say right at that edge between the past and the future. That's where we're at. We're always in the present, and that's known as location. If God were to stop the universe, right, from moving, every little bit of matter just stops moving, just freezes in place, we have no time, but what you have is location. Okay, everything is located. There's distance between everything, and there's location. That's all you have. That's the cross-section of time. Okay? That's the notion of cross-section of time. Okay, here we have Mr. Descartes. He came a couple centuries later, okay? And he does a little bit of analysis also on some of the basics of what he thought was physics. Remember, he was considered a philosopher, okay? I don't think he was, but he tried to do philosophy just like Aristotle. And their philosophy was geared or oriented towards physics, right? They wanted to understand how this universe works, and they called that philosophy. Okay, and I've dealt with that subject in the past, okay? But the issue is he wants to define motion, and he first defines informal motion, then he's going to define formal motion. Okay, so here's informal motion. Motion is nothing more than the action by which a body passes from one place to another. Okay, so he uses the word passes. Okay, so what is passes? It's motion. So they don't realize they're using synonyms to define the word motion. That's the big problem that all these people have. They never were able to separate the key word in their definition, which is already motion, some form of motion, and they never realized that they were saying it. And it happens to all of them to this day. A person seated, he gives an example here, a person seated in a vessel, which is setting sail thinks he is in motion if he looked to the shore that he has left and considered as fixed. He considers the shore fixed, okay? But not if he regard the ship itself, among the parts of which he preserves always the same situation. In other words, if he's inside, a lot of them have the same notion. Galileo also will have this notion. If you're inside a boat, right, inside the room of a boat, you're getting farther and farther from the shore than you're moving with respect to the shore. But you're not moving, supposedly, with respect to the little table that you have inside your room. That's what he's saying. And this is the notion that relativity is going to pick up on later on, because they're going to say, well, what's the frame of reference? Is it the shore or is it the table? That's what they're talking about here, okay? And he concludes, the person thus seated is more properly said to be at rest than in motion. He introduces the observer, seeing he is not conscious of being in motion. Again, very dangerous, because now he starts to introduce what the person perceives. And that's a no-no in physics. We don't care about your psychology, your philosophy. No, we want to see something objectively. We need to analyze something objectively. And, he's referring to what the person perceives. He says, oh, this is motion to him. Okay? And again, this is going to be a serious problem throughout, because to this day we have this observer problem. Physics, there are no observers. It's all objective, no subjectivity. So what's the formal definition? Well, here's Descartes' formal definition of time. And as you can see, I underlined a key word there, that transporting. Oh, isn't transporting already motion? See this, they keep messing it up and they don't realize it. Transporting of one part of matter or of one body from the vicinity of those bodies that are in immediate contact with it, or which we regard as at rest, which we regard, talking about the observer again, to the vicinity of other bodies. In other words, too many errors in these definitions because they're not careful enough in what they're saying. First, they introduce words that already embody motion, and second, they introduce the observer. And they're all the same. To this day, we have this problem, okay? And that's why mathematical physics cannot be part of science, great measure, because no definitions. And then what few there are, they introduce synonyms, and then it all comes down to opinions. They say, well, what did you see? How much time did you measure? Well, I measure so much time. Well, I measure some other. Well, you're correct and I'm correct. It's all relative. It's all relative. It's all relative, right? That's what it is. And so they leave it at that. And you walk out of there saying, what did we learn today? Okay, now we come to Mr. Galileo. He also analyzed time, motion, mainly motion. He was a motion guy, okay, like Descartes, more or less. And what does he say? Well, he said he defined two types of, or he distinguished uniform motion from accelerated motion. In other words, acceleration from just uniform motion, okay? The steady or uniform motion, by steady or uniform motion, I mean one in which the distances traversed by the moving particle during any equal intervals of time are themselves equal. So equal times, equal distance, etc., right? On the other hand, accelerated motion is said to be uniformly accelerated. Motion is said to be uniformly accelerated when starting from rest. It acquires during equal time intervals equal increments of speed. Okay, so it's speeding always at a given rate. It's going faster and faster and faster and faster. Okay, so he's talking about speed and acceleration. But see, the important part here is that he's introducing mathematics. He's throwing mathematics at the problem. You can see the title of his book, Discourses and Mathematical Demonstrations Relating to Two New Sciences. Yeah, he was one of the first to say mathematics is the language of physics, which it ain't, okay? But that's how you see where it came from. One important thing that you should know is that Galileo was not the first one to do the, in other words, he's credited with having thrown two balls from the Tower of Pisa, and letting them fall to the ground. One was big, one was small, and they both landed at the same time. So that's how he proved or demonstrated that lighter objects and heavier objects, barring any friction, fall at the same rate. Well, that's a misconstruction of history. It's tearing history to pieces. And so I just want to clarify that to whoever is interested in the issue. All these people here, they did the two ball, the small and big ball examination or test experiment before Galileo was born. Okay, we have John Philoponus in his theory of impetus, Domingo de Soto, a Jesuit, Spanish Jesuit, and he also talked about in his book, aside from the fact that he did the experiment, I think he was the first one to do it, the two balls. Okay. Girolamo Cardanus also wrote lots of stuff, hardly known by anyone, and he wrote tons. He wrote more than Galileo for sure. He probably was more versatile than Galileo. And for sure, Giuseppe Moletti, because Moletti, he was a professor at Padua University, which is the position that Galileo took over when this guy retired. So Moletti, he not only was there before Galileo, Galileo knew him. This guy wrote Dialogue on Mechanics. Galileo was interested in mechanics. It's almost impossible that Galileo never read his book, Moletti's book, or was acquainted with Moletti's experiments and his notions of mechanics. Okay, and if all that fails, we still have Simon Steven. He's a guy from Netherlands. Okay, and he wrote a book. You can find it on the internet, and about the weight of water. And in there, he does the experiment. In fact, he draws the picture of the tower and how he did the experiment. He did that in 1586. But that's when the book was published. He probably did the experiment 2 years earlier, about 1584, and Galileo was only 20 years old at the time. And so he was just getting out of school when this guy was already, publishing his book. So no way, Galileo was not the first guy to do the two ball trick, supposedly. What Galileo apparently did was the inclined planes. Okay, that was total. That was his stuff. He had his little. He was under house arrest at the last years of his life, and that's where he worked, and that's when he wrote this book, the one about the mechanics. Okay, motion. Okay, who came next? Well, one guy that comes next is this fellow. I guess everybody knows him, if I can get him up here. And his name is Isaac Newton. And what did Newton contribute to science, to motion, to gravity? Well, very little. He's credited with 3 laws of motion, 2 of which were already analyzed by Descartes before Newton was born. So, he was analyzed because his book was written like in the 1630s, late 1630s, and Newton was born in 1642. So, already Descartes had talked about 2 of his laws, the first and third law. Okay, those he analyzed before Newton did. And one of the reasons that Galileo became famous and why he's credited with everything is because of Newton. Newton read Galileo and quoted him quite a bit, and Newton was a god in his days. So because of him, we know Galileo. And we forgot about all these other fellows who did a lot of experiments. They already had a lot of the information that Galileo was later on going to publish, and I guess he got the credit, whether he requested it or not, he got the credit anyways, all because of this fellow. Anyways, one thing you should know about Principia, there are no equations. So Newton's equation, that came later. In fact, the French were the guys who came up with all his equations based on his book. Okay, so they put it into little variables and numbers and so on, and all these equations that they included later on. But no, Newton does not have, he only writes, he writes, he explains, okay? And, you know, he talks about 3 laws of motion. He never defined motion. He said, I do not define time, time, space, place, and motion, because we all know about it. We all know what they are. And so that's a bad way to start his book. He put that in his scholium. And so, you know, how can we credit him for the 3 laws of motion if he doesn't know or doesn't understand what motion is, if he can't define the word motion? And he never did. So we got very little from him in regards to motion. But here we've got a notion that he really had it wrong, and that's in his first law. He says, everybody continues in its state of rest. There's nothing at rest in the universe, so I don't know what he's talking about. Or of uniform motion in a right line, right meaning straight line. There's nothing that moves in a straight line, okay? And besides, straight is the wrong word. It's called rectilinear motion, but that's aside. Unless it is compelled to change that state by forces impressed upon it. And so, yeah, I don't know if we can credit him with the 3 laws of motion. That's the British claiming one of theirs wrongfully, making too much of Newton. But he did invent instantaneous motion, okay? And relativists don't like that, so they threw his instantaneous motion out the window. They said, look, nothing moves faster than light, okay? And so you're wrong, Newton. There's no instantaneous motion. Well, instantaneous means, again, cross-section of time. And all you have there is location, okay? So you can't have motion. You can't have instantaneous motion, because instantaneous supposedly is a cross-section of an interval of time. Whatever that could possibly mean. You're talking, again, location. What can instantaneous mean? So we have a contradiction when we use the word instantaneous in conjunction with the word motion. But other than that, Newton was right and relativists are wrong. And it's very easy to prove to all relativists on Earth that they are wrong. Okay? And the reason they are all wrong, they are irrational individuals, okay, is that weight is, using that term there, instantaneous, weight is instantaneous. Why is weight instantaneous? Because weight is location dependent. Weight is location dependent. An astronaut moves an inch, a tenth of an inch, a billionth of an inch forward towards the Earth. His weight changes instantaneously, to use that term. And we're going to explain that in 2 seconds here. So give me a little bit of time. I'll get there. Okay. Your weight changes instantaneously. That means that relativists are wrong. They talk about traveling faster than the speed of light or slower than the speed of light. That's because they're thinking that something has to travel. That's the problem. That's why they're wrong. That's why they're irrational, because they're using the particle hypothesis. They're saying that the particle from the sun cannot travel to the Earth instantaneously. And they're right. If the universe were made of particles, it wouldn't work. It wouldn't work because weight has to change instantaneously. As soon as the Earth moves an inch closer to the sun, it already has a different weight with respect to the sun. And you can't do that with particles. And that's the problem. The problem is, in other words, to put it in reverse, it's the instantaneous change in weight that destroys general relativity, because relativity is based on the field concept. And it's all these branches of mathematical physics, all these branches rely on the particle. So they want to explain everything with particle, with something traveling, okay? And that's where the problem is. You cannot explain it with particles. You cannot explain it with traveling. That's why you cannot explain weight the relativistic or mathematical physics way, okay? Okay, so where do we go after Newton? Well, from Newton we went to I mean, there were other people here, but here we go to Einstein and friends, okay? And what do they come up with? Well, they made a total mess of time and motion completely. First, they had motion through nothing. You move through space. Now, you can't move through space. You can only move through molasses. You can move through sand. You can move through water. You can move through air. You can move through a medium. If there is no medium, you are not moving through the thing, because it's not a thing. Space is not a thing. Space is absolutely nothing, that which has no shape. You cannot move through space. You move to some object. You move to the moon. You move to the sun or towards Jupiter. You have to move towards objects. People never learn to speak properly, and they say, oh, we move through space, so I'm in space. Now, you can't be in space because space is not a container. And this is part of the language problem that these people introduced with all their mathemagics. Okay? Motion through time, I don't know how you move through time. How do you move through time? Go back and kill your grandfather, kind of thing. How do you move through time? Take the time tunnel? Is that how you move through time? Time is a medium that you cut across, you slice in half as you move through it? Is that what time is? So the language is irrational. All that language is irrational. That's okay in ordinary speech. Don't bring it into science. Don't bring it into physics. Motion changes the rate of time. Here you have your twin brother, and he goes off to the stars, comes back, he's younger than you. So his motion, just the fact of him moving, changed time for him as for you, two different observers, but now we're not talking about observers. Now we're talking about reality. This guy comes, younger than you, looks like your grandson, he's your twin brother. Yeah, sure, maybe in Hollywood, please explain the metamorphosis, the physical process. That's what I need, okay? Time is a component of the surface or interior of the 4D universe within which we live, right? So, we talk about four-dimensional space-time, and you say, well, that's because you need four number lines to locate a point within space-time, right? But that's not true. See, good old Stephen Hawking, in his book, A Brief History of Time, he says he cannot imagine four-dimensional space. Four-dimensional space-time he was referring to. He's analyzing space-time. He says he cannot imagine it. Well, he's talking in terms of three-dimensional. He says he can imagine a three-dimensional something, okay? He can imagine a three-dimensional box. He cannot imagine a four-dimensional box. What is he saying? He's saying it's got four 90-degree angles to it. And of course we cannot picture that. So when they talk about that, they twist the language on you. They insinuate that they're talking about four coordinates converging upon a point. Okay, but then what they're really referring to is trying to imagine anything that is like that has length, width, and height, and a fourth dimension perpendicular to those three. And they say, well, yeah, you cannot imagine that. Of course not. And so, yeah, time in that sense becomes kind of weird, because now if time is something to do with motion, and time becomes this dimension that we cannot even imagine, or define for that matter, well then, yeah, we come out of those conferences not understanding squat. That's what it is, okay? And time slows down and accelerates, okay, depending on how fast you run. If you run close to the speed of light, well, time slows down and so on, And then you have, warped walls bend, raise, and beams. What is that about? Well, you had Arthur Eddington. He proved that Einstein was right, one of the first guy to prove Einstein right. And the way he did it, he said, look, you have this beam of light from a faraway star, and it bends, it curves around the gravity well created by the sun. The sun weighs down space-time, it bends it, right? And you have this ray, this beam go around. The problem is there's no physical object called ray or physical object called beam. What they're talking about is a shower of bullets. They're talking about photons. So the correct word is swerve or deflected. You can say that a photon was deflected by the curved wall of space. You can say that. But you cannot say that you bent time. So that you bent light, that you bent the beam of light. And so we've got a problem here because language is important here. It's important not because we're trying to beat up on semantics, but because the concept is wrong. You cannot say that you bent light. If light is a photon, if one little photon represents light, you cannot say you bent light because that's not what they're talking about. They're saying that the photon swerved or was deflected by the wall from its rectilinear path, as Newton would say. Okay, so the language is crucial. Okay, well, we start there with the irrationality of mathematical physics? No, we went ahead with Mr. Niels Bohr and his friends. Okay, the people from quantum. What did they come up with? Well, they came up with tachyons, for example. They travel faster than light, even though special relativity says nothing can travel faster than light. They say yes over here, and then when they're over here, they say, we clean our butts with the speed of light. We can go faster. So what are we supposed to conclude? I mean, they had to invent this particle to explain certain things, and these particles appear in peer-reviewed journals, in articles. They're allowed to put that stuff, even though on the other side they'll say, well, nothing can travel faster than light. So we have contradiction. People just live with the contradiction and say, yeah, that's okay, no problem. We love tachyons. They come from the future. Whatever, you know. And then we have the yo-yo effect. We have negative momentum transfer. You throw the ball, and instead of pushing it away, as you would think so, it carries negative motion. It delivers negative motion, and the pizza comes towards you. So if you want to pull on your pizza, you don't have to get an elongated, rope and just tug it over. No, you just throw a ball at it, and the pizza will come over. It's negative motion. Just make sure the ball has negative motion. That's what it's got to deliver, okay? Intangible action at a distance. Well, we have entanglement, and you have this particle over here, which affects this one over there, right? And they claim there's nothing in between. That simply this particle moves in some way and somehow affects the other one. So I call that, spirits? They call it energy. I call it spirits. Because what they're doing is black magic. They're not giving you a mechanism. They're saying this particle affects that one. So we have instantaneous motion, which they just denied. Now they're bringing it back, saying there's instantaneous motion because, if one goes clockwise, the other one is counterclockwise. If you turn the one that was going clockwise, if you turn that one counterclockwise, the other one instantaneously turns clockwise. So we do have instantaneous motion, and what happened to the speed of light, the fastest in the universe, the one that Einstein proved, and et cetera, out the window. That's what happened to it. Then we have bodyless movement. We have the photon. It's got no mass, no relativistic mass at least. It's got no mass and no rest mass, okay? And it's got no body. It's a point particle. So we have a nothing called the photon, bundle of energy or whatever, and it moves. It moves at the speed of light, 300,000 kilometers per second. So some weird things that we've got out there, right? Then we have the movement of concepts. I talked about that the other day. I'm not going to go in detail with that, but we have mass, energy. You move a mass, you transfer energy, you transfer information. Now, how's that for transferring concept? They transfer information. They extend the field. They move the charge. All these concepts are moving around all around us. You got to duck because you never know when one of these concepts might hit you in the face, And yeah, we have the warp wall, bend, rays, and beams also, okay? So, where does all this take us? Well, I just wanted to show that motion is still very weird. Time is still very weird. We have no idea what those are because the mathematicians never defined them. And they're fine with that because they can write a book like Stephen Hawking wrote his book, 180 plus pages, and he talks about time and he never defined the word time. So it's great because you can talk about time. You can use it in the equations as seconds, minutes, hours, years, whatever, and you never have to define it. So we never know what we're talking about, but we all talk about it. Time is what a clock measures or reads or whatever. Okay, so I just wanted to end this with this notion of the principle of equivalence. Okay, Einstein had a big problem trying to understand why the principle of equivalence works, and he just used that as that. He just mentioned it as a principle. He just took it as unfaith. He says, look, there's this principle that inertial mass is equal to gravitational mass under certain circumstances. And he could not explain it. He just said, I'm going to take it as a principle and just accept it, that that is so. Okay? And this is what the principle of equivalence says. Okay? Here you have accelerated reference frame in one on your left and rest mass in a gravitational field, okay, on the right. The first one deals with force equals mass times acceleration, which is Newton's second law. And the second one deals with his gravitational equation. And the first thing I want you to see here is that the arrows are always in the direction of push. Okay, so when the rocket on the left pushes upward, the ball comes down. Okay, and on the right hand, when the ball falls to earth, it's because something is allegedly pushing it from above. Okay, there's no mention of pull. And here you have maybe a better picture of that. Here's just a picture of it, okay? From the same fellow, you can see that when the rocket goes up and they talk about force equals mass times acceleration, all the arrows are pushing the ball downwards. They never thought of anything other than push because mathematical physics is a particle theory, all of it. 150% of it, whether it's general relativity and its field concept, or whether it's quantum mechanics and its tiny little balls of different names of balls that they have in the standard model. It's always push. That's why they could never figure out action at a distance. Okay, and so Einstein had a big problem with the principle of equivalence here because he says if you're in a rocket and you're being pushed at 9.8 d1 or 9.8 meters per second square, right, upwards that's the acceleration of your rocket, and you let go of the ball and the ball will come to the floor at that speed or at that acceleration rate, and if you're on the right and you're simply let go of the ball on earth, it'll fall with the same acceleration towards the center of the earth. So he said these two things seem to be equivalent. I don't know why, but I'm just going to declare it as a principle that they are equivalent. Okay, and of course he could never figure it out, never would, not with particles, because again you have problems explaining anything with particles, with discrete particles. How do we explain it in science, in real physics? Okay, here we go. This is the explanation for the principle of equivalence, and it's that if we have an atom, that red one there, and it's at a given distance from the Earth, there's a certain number of ropes at that distance connected between that atom and every atom on Earth. I didn't draw them all, by the way. Okay? And so, can you tell whether the ball is going upwards, leaving the Earth, or whether it's coming downwards? Well, under the rope model, it's no biggie. It's not even it's for babies. A 10-year-old can figure this out. The reason those two equations are equivalent under those circumstances is the same number of ropes converge upon that atom, irrespective of whether it's going out or coming in. At that location, you have a certain number of ropes. Okay? Further down, there are more ropes that widen up, because as it approaches, the ropes fan out. As it goes farther, the ropes, converge upon themselves. So at a given distance, if we could freeze the universe, we should be able to count every rope in there and say it's got gazillion ropes plus one, whatever. So it doesn't matter if the thing is going outwards or inwards. That's the reason, the cause, the mechanism that underlies the principle of equivalence, the number of ropes. It never occurred to them that Mother Nature does pull, and they never figured out how to pull because they never figured out the ropes. And why did they figure out the ropes? Because they said, well, I can't see them and I can't touch them, and they would be all tangled. I mean, nobody even proposed it because they probably dismissed it right offhand and say, well, yeah, we're not going to do that, right? And yeah, that's what it is. An object is not that which you can touch or see, it's that which has shape. The rope has shape, therefore it's a physical object. Now, do the ropes touch each other? Do the ropes cross each other? Can you touch a rope? Can you see a rope? That's a separate matter, okay? We've got an object that has shape, okay? We're done. And what we're saying is that gravity is the number of ropes converging upon an atom at a given distance. That's why your weight changes instantaneously. As soon as you move 1 inch closer to the earth, the ropes fan out. That atom is now connected to the gazillions of atoms, but now the atoms of the earth are not one behind the other. Now they've kind of separated with respect to your distance, to your location. Okay, and that's why the principle of equivalence works. It's the mechanism underlying the principle of equivalence. So yeah, if the sun were to disappear this very moment, no, it would not take 2 years for you to get the message. We would be running out of the solar system instantaneously because the ropes from every atom on Earth would have nothing to which they would be bound. The only reason the Earth goes around the sun is the sun swings the earth around itself through the gazillions of ropes that interconnect their mutual atoms. If you magically, God comes in, makes the sun disappear, every atom in there, all these ropes are just dangling there. They're not tied to anything, you start flying out, and so do all the other planets. So no, the notion that general relativity has that, it takes 8 minutes because for the information to reach you because nothing can travel faster than light, that's mentally retarded because it's based on the particle hypothesis, on traveling. Weight is not a traveling mechanism. Weight is a location mechanism. The closer you are to an object, the more the ropes fan out, and the stronger your acceleration towards that object. That's why it's acceleration is a distance phenomenon. It's a square of a distance phenomenon, right? And that also explains the principle of equivalence. If you're at a given distance, right, and you stop the universe, at that moment you freeze the universe and you count the number of ropes of that atom to all the atoms that make up the Earth, you should be able to count every single rope that is not what we call effective ropes, and that's a long story, but effective ropes. When that atom gets closer to the object, to the Earth, for example, now it's got more effective ropes. Why? Because one atom is no longer masked behind the other. Okay, we'll continue with this line of attack on the mathematical establishment. We're going to continue hopefully with some geometry and Aristotle and some of his friends from the Greek world. We'll see you on Sunday. Bye-bye.